Good morning, everyone. It's a great pleasure for me to be here and be part of this very great symposium. I'll do a few strange things today, because when Seb was asking for titles of presentations, I kind of submitted an abstract about stuff I was very enthusiastic about, which is related to polymer brushes. Then I realized the symposium was about biomimicry, and I thought, well, it doesn't really fit. I changed my title, but then I pulled it back to brushes. So I think that's going to be interesting. I want to start with a few remarks to thank a number of people. First and foremost, Seb, for inviting me to be here and to be part of this, but also to express my, appreciation for Seb's accomplishments, for his nomination to spend the year at Collège de France and be here, which I think is very well deserved. It's a recognition of his accomplishments, but it's also a great recognition of the field that he's been so active in. And so it's really a great pleasure to be here today. The second person I have to thank, without whom I would not be here, is Sam Stoop, because Sam is the one who brought Seb and myself together. So thank you very much, Sam. It's also really cool that basically all of us are here together. And before starting about science, I thought I want to start with a few slides, essentially going back down memory lane, to kind of contextualize some of the research I would like to share with you today. But I think what I would like to show is also maybe interesting to kind of connect some of the presentations you'll see today and maybe some connections between people. And my story today starts in 1996. I looked a bit different then. I had a few more hairs on my head. I was at the end of my PhD and trying to think what I want to do with the rest of the scientific part of my life. And I read this book by Jean-Marie Lane, which interestingly enough was also affiliated to Collège de France, so there are a lot of connections with this event. It's a really great book, and I read this book, and at page, I don't know what, my eye felt on a very small thing, two-dimensional polymers and a citation of reference 9.239. It was really just one sentence out of the whole book. It struck my mind. So I kind of looked up the reference, and it was a paper by Sam that was published in 1993 in Nature. And I was like, whoa, this is cool, because I was interested in organic molecules, I was interested in polymers, and this was really great stuff in between where people were trying to engineer small molecules to be assembled in very specific types of organizations to actually predict polymer properties or materials properties, which I found very interesting. And I thought, wow, this is interesting. Maybe I have a chance to do a postdoc with this professor in the US. At that time, there was no email, so I think I had to communicate by fax or by letters with Sam. I think it was a fax message. So I sent a fax message to Sam, and I asked him if he would be willing to support me to apply for a fellowship at the Science Foundation. Sam did not email at that time. I think Sam faxed back to me. And so he sent me some material to help me prepare a proposal to win, hopefully, a postdoctoral fellowship. So he sent me a draft of a paper that he, at that time, recently submitted for publication. It was about another self-assembly chemistry with materials which at that time Sam thought could be interesting for biomaterials, ferroelectrics, and other applications. So the material is really interesting. I used that, quote unquote, to write my proposal. I won the proposal, very nice. I was very happy that I could go to UIUC to work with Sam. And interestingly enough, a couple of months later, the contents of the proposal actually turned out to be the basis of this science paper that was published in 1997. And this is another example, I think, that shows the beauty of kind of programming self-assembly of small molecules. And this paper actually has another feature that has been in my mind for a long time. One of the cool things that this paper shows is basically how you can use molecular design to instruct materials to self-assemble in very particular organizations. And the one thing that struck my mind of this paper, that has been with me for about 3 decades, is the idea to kind of induce non-central symmetry in materials and to try to use that to harness nonlinear properties, be it optical or electrical or even polarity. So I came to Illinois, and then the idea that Sam proposed was to say, well, for this paper we worked on basically synthetic molecules. These are styrene, isoprene, flexible tri-block oligomers. Let's try to see if we can turn them into something biological. So that's basically what I started to work on. That's part one. Part two is basically in Illinois. I was also partnered up with a French guy in the same lab. So Sam somehow put the foreign postdocs far away in a chemistry lab. where we had a lot of fun. But it was scientifically very fruitful, and the two of us together, actually, I think we did really cool work. And if you look at, I think it's fair to argue what you see here, chemistry-wise, is somehow a transition between this 1997 Rothko paper of Sam and lots of this work on these peptide amphifiles that you're seeing today. So it's very cool to be part of this scientifically, but it was also a brilliant start of an amazing relationship with my best French friend, I would say. So Sepp and I, since 3 decades, have done lots of crazy, interesting things. Scientifically, personally, we went to many places. I could unfortunately not find photos which are older than this one. This is 2012 in the Forbidden City in Beijing. Sepp has a lot more hair. I already covered my hair. So thanks a lot, Sepp, again, for all the friendship and for inviting me to be here. So now moving forward to science. So what I want to talk about today is a bit kind of the main theme of the symposium today. But I'd like to talk a bit about surface grafting polymers from substrates. That's something part of my lab is very interested in. So basically what we do is we take an arbitrary surface, we modify this with molecules, which can either start a polymerization reaction or could act as a train transfer agent. And then we graft polymer chains from the substrate. And the unique feature of this is that these polymer chains are tethered via one chain end to the substrate. And since we grow them in a bottom-up fashion, we have the possibility to anchor these chains at distances which are much, much smaller than the radius of gyration, as a consequence of which we can enforce a stretched chain conformation. And this surface-initiated polymerization approach is very interesting. It has a number of unique attributes. It allows us to prepare thin films that present very high concentration of functional groups. This is interesting for diagnostics and all sorts of biosensing events. The stretched chain conformation of polymer brushes is also very unique, and it underlies properties such as unique non-fouling ability of these surfaces, lubrication properties. If you introduce appropriate functional groups, you can actually make surfaces that basically switch properties, because properties are often related to conformation. And since this is a wet chemical approach, it's also a very powerful methodology to modify conformal, complex, or structured or porous substrates. I want to add 2 more remarks to this. Very often when I talk about polymer brushes, there is still the perception that this is a chemistry that is kind of complicated, hard to scale up, and expensive. But if you look at the literature and at the evolutions in controlled radical polymerizations over the past decades or so, that's actually not true. Surface-initiated polymerizations are cheap, scalable, and you can actually conduct them and integrate them in continuous processes. And I just picked 3 examples of papers, not from our own group, to make this point. This is a nice paper from a group in Aarhus that was published a couple of years ago, where they show they can coat up to 50 A4 size steel metal plates under ambient conditions via controlled radical polymerization in a very effective way, very reproducibly, within half an hour time. And this reaction mixture is basically usable over 6 hours. Another interesting thing, if you look at the evolution of controlled radical polymerization methods, is illustrated here. That's basically the enormous decrease in cost per square meter if you think about surfaces, or chemicals per square meters if you think about surface-initiated polymerizations, which are actually due to all these refinements in catalytic methods. About 2 decades ago, a square meter of a brush would cost about $2,000 per square meter and would use about 10 liters of chemicals per square meter. Now we're down to 14 ml per square meter and about $2. And there are also nice examples where people show that you can actually integrate these chemistries with roll-to-roll processing and do things in a continuous way. But that being said, and now I would like to go back to some research, polymer brushes are actually hugely complex materials, and that's actually one reason why we are very interested in them, and also one reason why we're still conducting research on them. I very often use the cartoon on the left slide here to illustrate the brush, but this cartoon is obviously completely wrong and an absolute misrepresentation of the complexity of these materials. And a cartoon that much more closely resembles the reality is something along the lines as you can see on the lower left corner. So brushes are very complex systems. They are characterized by a clear non-linear decrease in polymer density as you move from the substrate polymer interface to the polymer air interface. There are living chain ends buried in the polymer brush that are responsible for this. There is a termination of living chain groups that also attribute to this. And as a consequence of this non-linear gradient in polymer density, there is also a non-linear change in conformation of polymer chains. These chains close to the surface are much more stretched as compared to those more far away from the surface. And the more you look at these brush systems and the more properties you try to investigate, the more complex things turn out to be. And the research I would like to share with you today is an example, I believe, that illustrates that actually how complex these systems are. And here we kind of go back, close the circle, to this 1997 paper by Sam, where I said I was intrigued by ferroelectricity, piezoelectricity, and pyroelectrics, and the idea to induce nonlinear properties. So I'd like to show two examples that illustrate how one can use, or that one actually can use, surface-initiated polymerization reactions to generate thin polymer films that present or possess spontaneous piezoelectric and pyroelectric properties. And I'll show you a few slides of context to kind of illustrate why I think this is quite interesting. Just 2 slides of context, just to make sure that everyone is on the same page. This is textbook know-how. But so I'll be talking about piezo and pyroelectric materials. Piezo and ferroelectrics are also referred to as polar materials because they typically, they possess an overall dipole moment, and in case of inorganic materials, this is due to a non-syntosymmetric crystal structure. Piezoelectricity describes this coupling between stress and electrical polarization. Pyroelectricity connects basically a voltage with a temperature change, either positive or negative. And ferroelectrics basically exhibit spontaneous electrical polarization that can be switched by an electric field. And so all piezoelectrics are also pyroelectrics. All ferroelectrics are also pyroelectrics and piezoelectrics. Examples of pyroelectric materials are typically inorganic materials, can be organic crystals, inorganics, but also a variety of polymers. And so polyvinylane fluoride is the most, I would say, well-known synthetic polymer that possesses these properties. But there is also a variety of biological materials like collagen and proteins that possess piezo and pyroelectric properties. So what's the challenge here from a polymer chemistry point of view? So inorganic piezo and pyroelectrics are typically crystalline solids, and they possess a non-centrosymmetric crystal structure. If we talk about polymers, this basically requires that these materials incorporate molecular dipoles, and we have to figure out ways to induce some sort of net polar order in these dipoles to generate an overall dipole moment. And to achieve this, in most cases, piezo and pyroelectric and ferroelectric polymers are usually pulled in an electrical field, sometimes utilizing mechanical stresses to enhance the alignment of dipoling and augment materials' properties. This is the polymer challenge. One way to get around of this is, of course, if you don't want to work with polymers, you can work with organic molecules and use self-assembly strategies such as we've shown here. That's another way to kind of obviate these poling processes. So what we kind of accidentally found a couple of years ago was that if you grow thin polymer films via surface-initiated polymerization, that this actually provides a route to produce very thin polymer films that possess pyro and piezoelectric properties. And I'll just walk you through a number of experiments, which were those experiments that kind of led us to this discovery, more or less. The work on here was done by a former PhD student, Jan Wang, who's now a group leader in Aachen, in collaboration with these people at EPFL and at UT in the US. So the story is that the student actually decided to prepare a number of different polymer brushes, strong polyelectrolytes, polyswitzer ions, neutral hydrophobic, and neutral hydrophilic polymer brushes. They were grafted from solid silicon substrates. And then, just out of curiosity, he started to investigate their pyroelectric properties in the setup shown here. So these polymer brushes are basically placed on a Peltier device connected to a circuit, and the idea was simply to expose them to an alternating temperature modulation, 1 and 2 degrees Kelvin up and down, and then try to see whether we can measure a pyroelectric current. And so what you can see on this slide is a number of examples of the evolution of the temperature modulation. That's in black. This is about 1 Kelvin up and down. And the corresponding pyroelectric current that we have measured in picoampere as a function of time for 4 of these samples. So if you utilize an hydrophilic hydroxyethylmethacrylate brush, there is no pyroelectric current. For an T-butylmethacrylate brush, there is no pyroelectric current. But for these strong electrolytes and these Witter ions, we do measure a pyroelectric current of a few picoampere. So this was an interesting observation. First of all, some brushes show this behavior, other brushes don't show this behavior. If you quantify this, the current for the strong electrolyte is about 4.5 picoampere, the Witter ion about 1.5, and the 2 others do not show any significant pyroelectric current. Then we did a number of control experiments to try to understand what's behind this. If you do the experiment for the unmodified silica surface, there is no current. If you take the surface modified as the ATIP initiator, no current. And interestingly enough, if you take the corresponding spin-coated polymer film, so if you don't grow METAC, the electrolyte, from the surface, but if you make it in solution and spin cast this film, you see a very weak to no significant pyroelectric current. And if you take the Witter ion, PMPC, and spin-coated, there is also no pyroelectric current. So the interesting observation by comparing the data sets on the top and the bottom here is that basically, apparently the brush architecture seems to matter. For the same polymer, the same chemical composition, spin coating for surface grafting makes the difference between a pyroelectric current and no pyroelectric current. Interestingly enough, the behavior for these films is quite distinct. For comparison, you can see here the behavior you would observe if you take a standard commercially available PVDF film. This shows your characteristic step-type function in the current as a function of temperature modulation. We observe a more triangular modulation. We believe that this has to do with the kinetics of the reversal of the polar order in the films, which is due to ionic dipoles in this particular case, whereas for PVDF this has to do with crystalline domains. The behavior we've seen for these Witter ions and electrolyte films is not unique, however. There are experiments being published where people looked at very thin protein films, so this is L-lysozyme, that also shows the same type of triangular modulation in current as a function of time. And so we think this has to do with the mechanism that is behind this, which is different from dipoles that are due to crystalline domains. Then we did a number of experiments to try to get some more insight as to what drives these observations. And an obvious thing to do if you work with electrolytes is to change counter ions. So we changed the chloride counter ions of these strong electrolytes with bromide, nitrate, isocyanate, and acetate. And the interesting observation is that here the type of counter ion basically affects the pyroelectric current that we change. So far we looked only at pyroelectric measurements. Then we also analyzed the same samples using piezoelectric force microscopy. Since these materials, when they show pyroelectric behavior, we anticipated also may show piezoelectric behavior. And the results of these PFM experiments actually confirmed what we saw from the pyroelectric analysis, in the sense that if you compare a strong electrolyte, a Witter ion, in this case a hydrophilic polymer brush, we see 0 inverse piezoelectric response for the neutral brush. We see a moderate response for the Witter ion and the strongest response for the strong electrolyte. And so this basically qualitatively agrees with the observations that we obtained from the pyroelectric measurements. We also looked then with PFM at brushes where we exchanged the counter ions. And the results from the experiments were also in agreement with what we observed from the pyroelectric analysis, in the sense that the inverse piezoelectric response that we measured depends on the counter ion that is in the film. So the PFM results kind of confirmed what we observed for the pyroelectric measurements. So so the observations of this, the conclusions from this are fairly obvious, I would say. I think this clearly shows that surface-initiated polymerization somehow allows to direct or induce a spontaneous polar order in these films, polar order of some sort. And this generates pyro and piezoelectric responses without the need for external fields to induce polar order, which I think is quite interesting. The big question for these systems, however, since they are polyelectrolytes, and polyelectrolytes are non-trivial polymers, I would argue, is to try to rationalize why these materials show this behavior. That's a very complicated question, and so here are a number of arguments that we believe underlie these observations. The first point is that polymer brushes generally are characterized also by a non-uniform dielectric profile that varies along the direction perpendicular to the substrate, so in the z direction here. And the consequence of this, we think, is that the strength of any dipole within a polymer brush will depend on the location of the film. So the strength of a dipole close to the substrate, we believe, is different from the strength of a dipole somewhat closer to the air. And this already would induce some sort of directionality in the layer. A second challenge or factor we believe contribute are counter-ion distribution and specific ion effects. So these brushes are characterized by a non-uniform counter-ion distribution. This is directly related to the non-uniform graphing density of these films. And the ion exchange experiments we've shown also show there are some sort of Hofmeister effects that are governing. The problem here is I'm very interested in kind of unraveling structure-property relationships, but politely put, polyelectrolytes are a bit complex to do this. So at the moment, these are the kind of hand-waving arguments that we believe kind of underlie this. So in the last few minutes, I want to show 2 or 3 pieces from new data that kind of substantiate these findings, and where we rationalized that this is kind of interesting what we observe on films containing ionic dipoles, but maybe things are easier to rationalize if you try to think about materials that include molecular dipoles. And interestingly, if I think about molecular dipoles, I close again the loop and get back to Sam, and I'll get back to it in a second. So the second question was, can we think about making brushes that contain molecular dipoles? Because then conceptually it would be easier to rationalize what's happening, and we could try to think about how to orient, for example, orientation of nitro groups in polymer films. So the system that we decided to explore is acrylonitrile. It's the monomer shown here. I forgot to add one introductory slide. We picked acrylonitrile because acrylonitrile is a very well-known piezo and pyroelectric polymer. The first data on these properties go back to the 1970s and 1980s. Sam Stoop worked on this during his PhD with Stephen Carr, if I'm correct, or I am correct. I was looking for your paper, but I had no access this morning, so I have a different paper on the slide. And acrylonitrile is a very interesting system because a nitrile group has a dipole moment of about 3.5 dBi. So the rationale was, can we utilize this as a monomer, polymerize this, and see if we could utilize surface-initiated polymerization to somehow induce alignment of these molecular dipoles. And interestingly enough, too fast. What we did was, so we grow very thin acrylonitrile brushes via surface-initiated polymerization from silicon substrates, and we did the same experiments as I've shown to you before. So this is the same type of setup we utilized before to probe pyroelectric properties. We prepared a polyacrylonitrile brush. It's about 10 nanometers in this case. We prepared a spin-coated polyacrylonitrile film, and the student also looked at a pooled, commercially available PVDF film. And these temperature modulation, current response curves are very interesting, I think. When you subject a polyacrylonitrile brush to a triangular temperature modulation or a square type temperature modulation, you see the characteristic pyroelectric response. Here we see a nice, in the upper right corner, a square wave response. And the intriguing thing is also, if you look at the lower right corner, the same experiment in the spin-coated film leads to 0 result. So there is an important influence of the architecture of the polymer, spin coating versus surface grafting, which I think is very intriguing. From the experiments here, if you change the temperature amplitude, if you go from 1 Kelvin per second to 2 Kelvin to 3 Kelvin, you can extract pyroelectric coefficients from the experiments. And as you can see here, the pyroelectric coefficient of a polyacrylonitrile brush is about 50 times 10 to the power minus 9 coulomb per square meter per Kelvin. which is comparable to a pulp PVDF film. But the interesting thing is basically this polyacrylic nitrile trap brush is only grown by surface-initiated polymerization, and we didn't have to apply an external field to achieve this. And of course, the spin-coated film doesn't show any of these pyroelectric properties. So I think this is conceptually maybe a bit easier to rationalize. We have molecular dipoles, and this indicates that basically this, the surface-initiated polymerization reaction somehow induces spontaneous pyeroelectricity. We have polarized FTR and also NEXAX experiments to back this up that indicate that if you look at the alignment of the nitro groups in these films, that there is indeed a net alignment in the brush films grown via surface-initiated polymerization, whereas there is actually isotropic orientation of dipoles in these spin-coated films, which I think is very interesting. So this brings me already to the end of the presentation. So basically, I kind of messed up my slides, I think. The right slide would have been, first of all, to kind of to make the point that I think surface-initiated polymerization is a very nice way to make films which are hugely complex, and if you dive deep, you find all sorts of interesting materials properties. That's conclusion one. The second point I wanted to make was just to thank Seb again for putting together this very nice day and for having me part of this. I also have to thank all my students and postdocs for doing all of the work, for making this possible, the funding agencies for providing our funding, and again, this was the slide I was looking for. Thanks, Seb, for inviting all of us.